Okay, I am going to walk you through big problem number 5. This is a polynomial that we're trying to find the roots and draw a sketch. And this is going to be a pretty long video because, as we know, the big problems have a lot of parts and some of the parts take a while. So let's get to it. Easy part to start with is we want to say how many roots it has. So you look at the exponent, the highest exponent, that is the degree of the polynomial. So in this case, that's a 5. And that means that it has 5 roots. And the next thing we want to say is how many roots are real versus non-real. And these are just the possibilities because non-real roots must come in pairs. There could be 0 non-real roots, and that means 5 would have to be real because the total has to add to 5. There could be 2 non-real roots, and if that's the case, then the number of real is 3. Or there could be 4 non-real roots in theory. Not that we're going to do a problem like that, but in theory, they come in pairs. So all these even numbers, 0, 2, or 4. And if there are 4 non-real roots, then that means there would be 1 real root. So those are all the possibilities, and we don't know what it's going to be for this problem yet. We're also going to do the general sketches. And what general sketches do is they remind you what the general shape of your graph should be when you get there, and also the end behavior. And we're going to have 3 general sketches because you have 1 general sketch for each row of your real and non-real table. So if the graph has 5 real and 0 non-real roots, that means it's going to have 5 x-intercepts. And the other thing we have to take into account is the sign of the leading coefficient. Because it's negative, we have a certain kind of end behavior. Just like a line with a negative slope, we're going to have this end going up and this end going down. So we'll connect that and we'll make it go through the x-axis 5 times. 1, 2, 3, 4, 5. There we go. And then for the second general sketch, same end behavior, but this time only 3 real roots, so 3 x-intercepts. So 1, 2, 3, and then you can make it extra squiggly or not, doesn't matter. And for the third general sketch, we have 1 real root, so only 1 x-intercept, but the same end behavior. So make it go through the x-axis once, and then you can make it do extra squigglies, like so. And the next step is to figure out the list of all possible rational roots. That's our APRR list. All possible rational roots. Rational roots are roots that can be written as a fraction. There could be other roots that are not rational, but we'll look for the rational roots first. And the way we do this is we find all possible numerators by looking for factors of the constant. So here's the constant, 72. We need to list all the factors of 72. So that's going to be a long list, plus or minus. And I'm just writing the plus or minus 1 time, but it applies to all the numbers. Plus or minus 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. Those are all the factors of 72. Now we're going to look for all the possible denominators. And these are going to be factors of the leading coefficient, which is -6. So plus or minus all the factors of 6. 1, 2, 3, and 6. So what we have to do is put together all those numerators over all those denominators in all the possible combinations, which sounds like it's going to be horrendous, but a lot of them are going to be duplicates. And so we're going to do this systematically. First, I'm going to put all the numerators over 1. So that's just going to give me 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, 72. Next, I'm going to put all the numerators over 2. So 1/2. The next one is 2 over 2, but that's just 1, and we already have that. 3 over 2. 4 over 2, we've got 6 over 2, we've got 8 over 2, we've got 9 over 2. is new. 12 over 2, 18 over 2, all the rest of them we already have that number. So we're done with the denominator too. Now we put all of the numerators over 3. So we have 1 over 3, 2 over 3, 3 over 3 we have 4 over 3 is new. 6 over 3 we have 8 over 3 is new. 9 over 3 we have 12 over 3, 18 over 3, all the rest of them we have. So let's move on and use a denominator of 6. All the numerators over 6. So 1 over 6. 2 over 6 we have 3 over 6. We have 4 over 6. We have 6 over 6. We have 8 over 6. We have 9 over 6. We have everything else. So I believe that's it. Okay, so great news. We have just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 times 2 for the plus or minus. Only 40 potential rational numbers as roots compared to the infinitely many rational numbers there are. So we've narrowed it down quite a bit. Next, we're going to make the synthetic division chart. And in the synthetic division chart, we will see hopefully some roots and also some clues to get us to the rest of the roots. So give yourself lots and lots of space. Give yourself room for plenty of rows above and below the 0 row. So just as a reminder, you're going to put a 0 row in the middle, somewhere with lots of room above and below. And then the coefficients of the polynomial, -6, 11, 94, -205, -66, and 72. 72 would be the remainder if you were dividing by x minus 0. So I'm going to cordon off the remainders into their own column. And you always want to make the 0 row stand out because you're coming back to the 0 row every time you make a new row. So if you use a highlighter or if you perhaps use a different color or just lines around it, something to make it stand out. Okay, now I'm going in order. I'm not skipping around, and there are important reasons for going in order, primarily because if we don't get zeros over here in the remainder column, we might get some other kinds of clues that will help us to find the zeros, and if you don't go in order, you're not going to notice those clues. So the first thing I do is make the row for 1. Put the 1 in the box, bring up the -6. And now I'm going to talk through this row just as a reminder, but I won't talk through every single row. So -6 times the number in the box. Add the next number in the 0 row. -6 plus 11 is 5. 5 times the number in the box. Add the next number in the 0 row. 5 times 1 plus 94 is 99. Don't rely on doing this in your head. Use a calculator. 99 times the number in the box plus the next number in the 0 row. -106. -106 times the number in the box plus the next number in the 0 row. -172. -172 times the number in the box plus the next number in the 0 row. -100. Okay, so we did not find a root. However, something important did happen. Notice that right here, the sign of the remainder changes from positive to negative. That means, remember that the remainders are also the y-coordinates of the points, and that means the y-coordinates changed from positive to negative. And the only way for that to happen is if the graph passed through the x-axis. So there is a root in between there somewhere. We're not going to go looking for it yet. We're going to hold off on that and do some more integers going in order. So I'm going to go ahead and do the 2 row and the 3 row and the 4 row. -1, -2, -3, -4. Yes, this is going to take a while, but you have to stick with it. I would say in general, you're not going to have to go beyond this, and sometimes not this much, but this is a more difficult problem. I'm going to go ahead and pause, fill in all these numbers, and then we'll move on from there. Okay, check this out. We have a whole bunch of rows filled in, and we have some really large remainders, so pretty big y values of points. That's okay. Notice what we found here. Right here we have a root, so that is a celebration. Yay! So x equals 3 is a root. Okay. Now, I went a row beyond 3. I did the 4 row, and there's something significant happening here, which I'm going to come back and talk about in just a minute. Also notice down here we have 72 and then we have negative 144, another sign change. So another root is happening somewhere between 0 and negative 1 because of change from positive to negative. So there is a root between 0 and 1. There is a root between 0 and negative 1. We don't know if those roots are rational. They might be irrational. And so we can't necessarily find them by just trying all the fractions. We might end up trying some of the fractions. Notice that my remainders were getting really big here. I was getting discouraged, like there is no way that's going to turn back around and go back to 0, but then I did the negative 4 row and it actually did. So how do you know how far to go? Here is something that I have noticed. I've noticed when using positives that when all the signs are the same, negative, 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 or if it was positive, 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 then I haven't noticed it turn back around. That's pretty much the end. But on the other hand, when you're plugging in a negative root, I notice that it's continuing to change generally until signs alternate. So this goes negative, positive, negative, negative, positive. Those are not alternating. If I got down to the point where it went negative, positive, negative, positive, negative, then I would be pretty sure it's not going to turn back around. But in general, go to 4 if you have to. I'm not going to give you problems that go way beyond that. Okay, so we have our second root here. So we have 2 roots. And how many roots are there for this problem? 5. If you have 2, how many are left? 3. Okay, so you can't whittle it down to a quadratic until you have only 2 roots left. So we still have to find a third root somehow. And this is where I would start trying fractions. I would not try fractions until this point. But we know we have to find a third root. We know there is a root between 0 and 1. It could be a rational root. And the choices we have that fall between 0 and 1 are 1/2, 1/3, 4/3, and 1/6. So I would start trying those and see if any of them work. We also know that there is a root between 0 and negative 1 because of the sign change right here. So we could try fractions that fall between 0 and negative 1, negative 1/2, negative 1/3, negative 2/3, negative 1/6. I'm not going to show you all of my attempts and all of the fails until I finally find one. I'm going to show you the one that I finally found that worked. Now maybe this is the one you would try first and it works, or maybe you don't try this until the 3rd or 4th or 5th fraction attempt, but look what happens. And I'm going to go ahead and put it right here in my chart. Negative 2/3, bring down the negative 6, multiply that by negative 2/3, add the 11, and you get 15. Multiply that by negative 2/3, add 94, and you get 84. Multiply that by negative 2/3, add negative 205, and you get negative 261. It's a really good sign that these are working out to be integers. As soon as they start to be fractions in here, you know that row is not going to work out. Don't waste your time on it. Don't even finish the row. Just move on to a different fraction. Okay, negative 261 times negative 2/3. Add the next number, negative 66, and we have 108. 108 times negative 2/3. Add 72, and we have 0. So we have a third root, negative 2/3. Okay, now that we have 3 roots and there are only 2 roots left to go, let me show you how you whittle your polynomial down to a quadratic. So what we're going to do is choose any one of the 3 rows that has a root. I'm going to choose this row, the negative 2/3 row. The numbers in this row represent the 4th degree polynomial that's left over after dividing by x plus 2/3. So take a different root, like negative 4, divide it into this roots row. Do that over off to the side. Negative 4 divided into negative 6, 15, 84, negative 261, 108. Bring down the first number, multiply by negative 4, add 39 times negative 4 is negative 156, add negative 72 times negative 4 is 288, add 27 times negative 4 is negative 108, add 0. Okay, we were expecting a remainder of 0 because we knew negative 4 was a root. The goal of doing that was to find these numbers here. That would be the remaining cubic. So we started with a 5th degree polynomial. Dividing by one root, gives us a 4th degree polynomial. Dividing that by another one of our roots gives us a 3rd degree polynomial. So guess what we're going to do now? Take the other root that we haven't used yet, which was 3, divide 3 into this remaining cubic, and I could do it right here. 3, bring down the negative 6, multiply by the number in the box, add, multiply by the number in the box, add, multiply by the number in the box, add, remainder 0, of course, we were expecting that because we knew 3 was a root, but what we were going for is this set of numbers, that's our quadratic, negative 6x squared plus 21x minus 9. We're going to set that equal to 0, and we're going to find our two remaining roots. So let's make this easier on ourselves and divide everything by negative 3. 2x squared minus 7x plus 3 equals 0. Now that may or may not be factorable. Of course, I've already done this problem, so I know that this one turns out to be factorable. But if it's not factorable, you want to use a quadratic formula. So let's do 2x times x, and then a 3 and a 1 minus minus. That works out. So set each of those equal to 0. And you get 1/2 as one of the other roots, and you get 3. Okay, let's look back at the chart. Remember how we had a sign change between here and here? So that told us that there would be a root between 0 and 1. The bell's ringing. Okay, 1/2 is that root that falls between 0 and 1. And there was one other trend in the chart I wanted to show you. So back here, when we found this root, the remainders went negative, 0, negative. That is a clue that you could have a double root, because if your y values go from negative to 0 to negative, the way that could happen is if you just go up and just touch and come right back down, and when that happens you have a double root, which is what we got. X equals 3 is another root, and we already had x equals 3. Another thing that could happen is you could go up through some other place and come back down, meaning there's another root that falls between here and here, whatever that is. In this case, it would be between 2 and 4. So if I make my graph a little bit more specific, we have, for this problem, we have 2, 3, and 4. We had a negative y value, 0, and another negative y value. And one possibility was it just comes up and just touches and goes back down, and that's what happened for this problem. But another possibility is it goes up through some other number between 2 and 3 and comes back down. And a third possibility is that it goes up through 3 and then back down through another number that falls between 3 and 4 and comes back down. Those are the only 3 possibilities, and in all of those possibilities we found another root. We have the original root at 3, and we either have another root at 3 or we have something else between 2 and 4. So anytime you see negative, 0, negative, you want to think to yourself, that means something. It could be a double root, or it could be an extra root something else that falls between 2 and 4. Okay, that same thing is true if it goes positive, 0, positive. So if you ever see negative, 0, negative, or positive, 0, positive, you can expect either a double root or an extra root in there. Okay, this is a very long video. There is one thing left to do to complete the problem, and that is to, well, I should write the 5 roots down, first of all, to finish that part. So the roots were, remember, roots are also called zeros. So we had x equals 3. X equals 3, again, I list it twice to make sure I have all 5. 1/2, negative 2/3, and what was the other one? Negative 4. It doesn't matter to me what order you write these in, as long as you have all 5. Okay, next thing we're going to do is draw the graph. And so let's get a new piece of paper for that. And let's see if we can see both at the same time. Okay. So you want to look at your x coordinates that you used, numbers like 0, 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5, etc. And you want to look at the y values, the remainders that you found. These numbers are going to determine your scale on your y-axis. And it looks like for this problem I need to go maybe to, I need to go down as far as negative 1764. So for my scale, we're going to do something like, my computer's going to lag, so this is going to be a little slow. Let's go with single screen, and let's do 1, 2, 3, 4, 5. And negative 1, negative 2, negative 3, negative 4, negative 5. And then let's do something like 500, 1,000. Okay. So make sure you plot all your roots. So we have x equals 3. We have x equals 1/2. We have x equals negative 2/3. And we have x equals negative 4. Then you want to use the numbers in your chart to give you other points. So we have the point 4, comma, negative 784. That would be around here. We have the point 3, comma, 0, got that. 2, comma, negative 144. That would be up here somewhere. We have 1, comma, negative 100. We have 0, comma, 72. We have negative 1, comma, negative 144. We have negative 2, comma, negative 1,000. Negative 3, comma, negative 1764. Negative 4, 0. And that's about it. Okay, and then look back at your general sketches and make sure that your end behavior is correct and make sure that makes sense for what you're drawing. So we have something like, remember for a double root it comes up and touches and goes right back down. Or if it's coming from above, it just comes down and touches and goes right back up. Okay, there's our graph. Okay, I would recommend you come back to this video over and over, even if you're working on a different problem, just to get some of the concepts down. The concepts of sign changes, of looking for a double root or an extra root, and of whittling your polynomial down to a quadratic by dividing into one roots row the remaining roots and whittling it down further and further. Because all those things will come up as the problems get harder. It will be helpful to use those techniques again. Good luck.